Okay, so section 4.7 is about inverse trig functions. So we're going to first talk through just inverse functions and what that means, and then we'll talk about that in the context of trig. So suppose you have this function f of x. One way to think about this is that it takes x values as inputs and returns y values as an output. So I usually draw this with a diagram. These are the input values. F takes them to some output value. This is your function f. What f inverse is going to do is go this way. So basically the domain of f is the range of f inverse. So it undoes the function f. Another way to think about that is like, I talked about it in college algebra as like shoes and socks. When you put your socks and shoes on, the inverse of that, what would undo that and give you back and get you back to where you started, is taking your shoes off and then taking your socks off. I'll come back to this diagram in just a minute, but so we have f of x is 2x plus 3 f inverse. One way to do this that you probably learned in college algebra was to change f of x to y, then switch x and y, and then solve for y. So x minus 3 divided by 2 is y, and then call that f inverse of x. Or another way to do this would be to write down the steps for f. So for f, you would multiply by 2. The first thing you would do is multiply by 2. The second thing you would do is add 3. So for f inverse, you would undo those in the opposite order, just like your socks and your shoes. You put on your socks, then you put on your shoes. To undo that, you take off your shoes first, then take off your socks. So reverse steps in the reverse order. So you would first subtract 3 and then divide by 2, which gives you x minus 3, divided by 2. This is f inverse of x. So think about, this is A maps to B under F, but B maps to A under F inverse. Okay, so trig functions work similarly. So let's first talk about what a trig function is actually doing. Let's be reminded about that. So you have like sine of 60 degrees gives you root 3 over 2. The sine of some angle gives you a number. So your picture would look like this for sine. These would be angles to numbers for sine of x. So sine of 90 degrees, sine of 120 degrees, sine of 60 degrees, whatever. It takes those angles and gives you the sine value at the angle. So it's giving you a number at that angle. So what we're going to do now is to sort of do that backwards. So we're going to find angles that give certain trig values. So where is sine of x equal to a half? So we're solving this equation, sine x equals a half. And what that's going to do is basically we're taking that 1/2 and we'd like to get the angle that got us there. So that's going to be sine inverse of x. Let's first talk through what that actually, like how we could answer that question now. So the sine of some angle gives us a half. So those angles, x could be pi over 6, 5 pi over 6, and then any coterminal angle with those. So 13 pi over 6, 5, 12, 17 pi over 6. All of those would give you a sine value of a half. That's a problem, right? That I've asked you this one question: what angle has a sine value of 1/2? Well, the answer is that there are infinitely many of them. So it's a hard question to answer. So what we want to do is sort of restrict ourselves. So let me talk through sort of a little bit about that. So looking at 1/2, y equals 1/2, that's all in here, right? That's on that line. So it's this angle, this would be pi over 6 here. This one's 5 pi over 6. And then it would happen again here at 13 pi over 6. You go negative as well. So there are infinitely many times that this graph will go through 1/2. So we can find lots of them. So the problem is that there are so many angles that have that same sine value, so the inverse isn't a function. And think about that. If you remember in college algebra, for a function to have an inverse, it has to pass the vertical line test, that makes it a function, and the horizontal line test. This is because when you do an inverse, you're switching x and y. So if your function you're starting with passes the horizontal line test, then when you switch x and y, it will pass the vertical line test, meaning that the inverse will be a function. So what we want to do is figure out where can we restrict this domain for sine so that we could pass the vertical and the horizontal line test. So like here would be a place that passes the horizontal line test. It doesn't, like this piece fails it, right? Because it intersects that horizontal line twice. So we want to figure out a piece of this graph that gives us all of the information that we need, all the possible values for sine, positive and negative. So this would work, right? It goes peak to valley, passes the horizontal line test. But this is actually quadrants 2 and 3. This is Q2 and Q3. This would be quadrant 1. And this is quadrant 4, but so is this, right? So basically, to use this piece that we're on right now, to use this piece, I'd have to go through quadrant 1 and then use just quadrants 2 and 3, and that's kind of clunky. So instead of that, we're going to choose a different piece that gets everything. This one. This piece gets all of the stuff for sine, all the negative values and all the positive values. It passes the horizontal line test, so the inverse would be a function. So that's what we're going to do. Restrict to negative pi over 2 to pi over 2. That's the quadrants 4 and 1. So on this restricted domain, sine is 1 to 1. That means it passes the horizontal line test. So you can find an inverse function. We'll call it inverse sine. We're going to write it sine inverse of x. So sine inverse of root 3 over 2, what you're going to do is ask yourself, okay, sine of what angle theta equals root 3 over 2? Theta, so sine, we're only looking in quadrants 1 and 4. Sine of sine of theta is root 3 over 2. So it's a tall angle and it's positive, so it's in the first quadrant. That's our 60-degree angle, right? So 60 degrees or pi over 3. On this one, sine inverse of negative root 2 over 2. So I would rewrite this as sine of some angle theta is negative root 2 over 2. The fact that it's negative means that we're down here. Again, I'm not messing with quadrants 2 and 3 because my restriction here is that I should stay in 4 and 1. And that is because we need to pass the horizontal line test to be able to talk about an inverse function. So sine of theta is negative root 2 over 2. That's going to be this angle right here. That's theta. And we're going to use that as negative 45 degrees. Or negative pi over 4 radians. Now, you may ask yourself, okay, well, why wouldn't you call that 7 pi over 4? And that's because basically we don't want to, if I was to do that, I'd have to go through quadrants 2 and 3 to get there. And what we've done is say that those don't exist. So instead of going through 2 and 3 to get there, we're going to go this way to get there. I'll go back to that graph and show you that as well. So instead of going here and then traveling through both of these to get to that quadrant 4 angle, you're just going to go backwards and get it right here and pick it up at negative pi over 4 so that you stay in that green chunk on our graph. All right, so negative pi over 4, pi over 3, and then lastly we have sine inverse of negative 1. So again, I'm going to rewrite this and say sine of theta is equal to negative 1. Then I'm going to draw a picture. Sine is negative 1 down here. It's sine inverse, so I know I shouldn't go through 2 or 3 to get there. That means I need to do this. That angle is negative pi over 2. So that is just some examples with sine inverse. We can do a similar thing with cosine. Again, we need to pass the horizontal line test and get all of the stuff that we need. So this would do it. This would do it. This would do it. You may think, okay, let's do the same thing we did for sine and restrict to 4 and 1. But remember, cosine's positive and 4 and 1, so that doesn't work. But we will use this. That's quadrant 1 and quadrant 2. So we're going to restrict to go from 0 less than or equal to theta less than or equal to pi. So quadrants 1 and quadrant 2, the top half. So for sine inverse, you use the right half, quadrants 4 and 1. For cosine inverse, you're going to use the top half. All right, so again, rewrite this. Cosine theta is root 3 over 2. So this is cosine, so I'm using the top half. That's what we just chose, quadrants 1 and 2. Where is cosine root 3 over 2? So cosine is positive in the first quadrant, and root 3 over 2 means that x part's big, so it's this angle. So theta is pi over 6. Here I rewrite cosine of theta is equal to negative root 2 over 2. Well, negative root 2 over 2, cosine does that over here. Again, we're not using the bottom half of the unit circle. So negative root 2 over 2 is this angle. That's where cosine does that. That is the pi over 4 in quadrant 2, so 3 pi over 4. Cosine of theta equals negative 1. Again, we're not using the bottom half. Cosine is negative 1 here, and that angle is pi. So, here, let's walk through this one. We have 2 cosine theta minus 1 equals 0. We're going to solve for theta between 0 and pi. This is a preview of what is to come. So 2 cosine theta equals 1. Cosine theta equals a half. So theta, where is cosine 1/2? We're not using the bottom half. Cosine is a half right here at pi over 3. Okay, this asks between 0 and 2 pi. This is the answer between 0 and pi. 0 and 2 pi, we would pick up the other time that cosine is positive, which is down here. So this would be theta equals pi over 3 and 5 pi over 3. All solutions would be those plus, let me see if I can write this better, this and all coterminal angles. And we'll talk more about how to write that soon. All right, so a function and its inverse undo each other. With that in mind, sine inverse of x is just x. When you compose f and f inverse, you get back what you started with. And this works both ways. F inverse of f of x, you get x back as well. All right, so sine of sine inverse of x equals x, cosine of cosine inverse of x equals x, sine inverse of sine theta is theta, cosine inverse of cosine theta is theta. X here is a number, theta is an angle. So we want to find these sine inverse of a half. Well, if these undo each other, this should be 1/2. But to convince yourself of it, sine theta is 1/2. Theta is pi over 6 then. So sine of theta now equals sine of pi over 6, which is a half. Right, sine inverse of a number will give you an angle. So that's what I just did here. This whole thing I replaced with that angle pi over 6. All right, cosine inverse of cosine of pi over 3. Cosine pi over 3. What is the cosine of pi over 3? It's 1/2. And then cosine inverse of a half. Where is cosine half of pi over 3? All right. Let me draw one that is a little bit trickier. Let's do cosine inverse of cosine of 5 pi over 3. So what your gut should say to write down 5 pi over 3, but that's actually not right here because of the cosine inverse restrictions. So cosine of 5 pi over 3, 5 pi over 3 is this one down here. Cosine there is 1/2. Cosine inverse of a half is just pi over 3, right? Because cosine inverse can't be down here. Cosine inverse of a half is that angle there is pi over 3. So just be careful about where the angle is. You can work these out so that you make sure you don't miss something like that. 3 and 4 are some of my favorite questions. You take this idea and you use it for triangles. So take the inside here. This is the same thing that sine of theta is 5/13, and use it to draw a triangle. Sine inverse restricted to 1 and 4. This is positive, so that means we are in quadrant 1. And sine of theta is 5/13, so opposite over hypotenuse. Use that to find the other side with the Pythagorean theorem. This is 12, that's a Pythagorean triple, 5, 12, 13. So we've rewritten this whole thing as that angle, cotangent of theta. This is theta. What is cotangent of that? It's 5/12. 12/5, sorry. X over y. So again, Pythagorean theorem gives you that third side. And then, start by rewriting using this fact that sine inverse of a number is an angle. So we've replaced this whole thing with this angle in this picture. So cotangent then would be adjacent over opposite, so 12/5. And you're going to do a similar thing here. Sine of theta is x over 1. That's what we're going to go with and how we would rewrite that. So we've done this now. We'll have cosine of theta after we draw a picture. Sine again, so it can't be in 2 or 3. And we're going to assume x is positive, so we'll just put this picture up here. So we've got opposite over hypotenuse, and then we would need to find this missing side. So Pythagorean theorem says 1 squared equals x squared plus a squared. So 1 minus x squared equals a squared. And then that gives us that a is plus or minus the square root of 1 minus x squared. That is in the right direction, so it would be positive. All right, so then, let me move this out of the way. So cosine of theta, now we're looking at cosine of that angle, which would be adjacent over opposite. So 1 minus x, the square root of 1 minus x squared over 1. Number 5 is similar to what we've been doing. We have a 10-foot ladder leaning against a wall. I should draw here's the wall, here's the floor, here's the ladder. It's a 10-foot ladder, yes. So we got a 10-foot ladder, and it's 5 feet from the wall. The foot of the ladder is 5 feet from the wall. Draw a picture to visualize this. What's the angle between the wall and the ladder? So we're looking for this angle theta. Sine of theta, opposite over hypotenuse, is 5/10, which is a half. So sine theta equals 1/2. To solve this, we're like using inverse trig, but we can do this, right? Theta is, sine is 1/2 here at 30 degrees. Okay, so the same thing can be done for tangent. You want to restrict it to a piece. Tangent follows sine, so it's going to be restricted to quadrants 4 and 1, just like sine. That's all we really need to know. But you can use that to do something like this, which is fun. Tangent of theta is equal to x over 1. So then we've rewritten this as secant of theta. So tangent of theta is x over 1. So we're going to draw a picture. It's tan inverse, so we know we're not going to be in 2 or 3. And we're going to say that tangent, that x is positive. So we'll put it up here in quadrant 1. Tangent is opposite over adjacent, so this is x into 1. And then use that to find the hypotenuse. So 1 squared plus x squared equals c squared. So c is the square root of 1 plus x squared. And then we want to do secant of that. So 1 over cosine, which is adjacent over hypotenuse. So we're looking at hypotenuse over adjacent. So the square root of 1 plus x squared over 1. This is thing. All right. So some of that was fast, but pause it and rewind it and email me questions if you need me. I will be happy to help you.